Welcome everyone to the inaugural session of the AIMEDx webinar series. My name is Hongliang Xin. I'm professor of chemical engineering at Virginia Tech. It's my great pleasure to introduce our speaker, Professor Gabor Csanyi from University of Cambridge. Originally from Hungary, Gabor earned his bachelor degree in mathematics at Cambridge in 1994. Then he traveled across the Atlantic to another Cambridge, MIT, where he completed his PhD in computational physics in 2001. Afterward, he returned to Cambridge, where he did postdoc research in the Cavendish laboratory. He is currently a professor of molecular modeling in Cambridge Engineering Department. Professor Csanyi is widely regarded as a pioneer in machine learning molecular dynamics for material science. His research group has developed Gaussian approximation potentials, or GAP, the maze architecture, and many others, which have enabled quantum accurate simulations at scales. His current research focuses on foundation models for atomic systems, a topic he will delve into in today's webinar. So without further ado, Professor Csanyi, thank you for joining us today. The virtual podium is yours.
Thank you. I'm glad to share the screen again. Here we go. Okay, do you see the screen?
Yes.
Yeah. Okay, let me just get rid of some windows that are bothering me. Okay, so good. I can't remember exactly what title I gave, but foundation models from molecular dynamics or for materials chemistry is what I typically call this research. So I want to start with a simple multiple scales of modeling slide, which you've seen many of these eventually over the years. But the important thing is that these are that we want to go from below. So a lot of these model methods that are here, they span like length scales, time scales, and errors. But a lot of the models, especially up here, are parameterized from above. So, and that's how most of science is done. So you want to attack some question, you create a model, you set the parameters of that model to reproduce some sort of milestones, landmarks of your which you know, and then you use your models to study the details. But first principles modeling, and as has been done for the past I don't know, 50 years, is different. You start from below, you start with quantum chemistry, with the Schrödinger equation, you know that is true, and then you integrate out various degrees of freedom. So when you integrate out the wave functions and you focus on the electron density, the one electron picture, then you get density functional theory. When you integrate out electrons from that, you are supposed to get to force fields, so atoms which just feel the forces from the other atoms, and so on. And really, I want to reclaim this word. It's normally applied to electronic structure methods, but I think this idea is very general, and you should be able to go up all the way. And in particular, this step of leaving electrons behind and going to force fields has really not been done before ML potentials in a first principles manner. So what we want to do is this step, is to go to build force fields that are built from either density functional theory or lower length scale accurate electronic structure models, but giving the energies and forces that those models give. But at the speed of empirical force fields, a million times faster, because we don't deal with the electrons anymore. So we are losing something when we do this. We lose the electronic degrees of freedom on purpose. We won't be able to ask questions about the electrons, but questions about atoms and their trajectories, we should be asking at this level rather than with electronic structure theory. And so we want to do that with no loss of accuracy. Just to roll back a bit, without these ML models, if you wanted to know where the atoms are in a material, in a process, you're left to do ab initio molecular dynamics, so full electronic structure molecular dynamics. And this has really grown up in the last few decades as a microscope for atomic scale processes. So you can compute phase diagrams with it. Here's the phase diagram of carbon. You can compute aqueous solutions of ions, polyatomic ions, and get it right. Get for example, this the experiment versus theory of the ionization potentials, and then study the detailed structure that you don't have experimental access to. And of course, surface science is a huge area where you can experimentally access almost atomic resolution, but not quite, nanometer resolution processes, but the atoms are 10 times smaller. And so if you want to know exactly how bonding takes place on a surface, how reactions happen, then you have to use modeling. And the density functional theory in particular has emerged as an excellent tool for doing that. So overall, nowadays people use first principles MD to compute a vast range of material properties in a predictive manner. So stability, thermal stability, dynamical stability, catalysis, efficiency and selectivity of heterogeneous catalysts. Drug properties can be computed, their solubility, metabolic processes on drugs, and semiconductor defects. Again, these are just a random set of examples that I drew here. This is doing ab initio molecular dynamics is a huge part of computational science. So this is the fraction of use of the UK National Academic Computer Facility, and 35% of that is just straight DFT molecular dynamics with VASP. If you add up all the other blue bits, you get to about 40%. So 40% of the UK's academic computing is used to do ab initio MD. And what is that? So you have the positions R of your atoms. You compute the Schrödinger equation in some approximation, typically density functional theory, wave functions, densities. From that, you compute forces on ions, and you solve Newton's law and get new positions. And you go round and round again. And this is, say, very predictive, highly accurate, but in some ways a colossal waste, because you need to throw away all these wave functions and densities and all the detail that you've computed very expensively, and the only thing you keep are the forces. So really, the idea, instead, you should just go from positions to forces, using some kind of functional form, some kind of analytic formula, which should then be much, much more efficient. And of course, what really I'm talking about is a mapping from the nuclear coordinates to the energies. So it's R to the 3n to R. And if you have that, then you can run dynamics. And of course, this is not a new idea. So quantum chemists have been doing this for many, many decades for small molecules. And it is systematic, exceedingly accurate, can be more accurate than experiment, but scales exponentially with system size, the traditional methods in the way that quantum chemists have been doing this. So the question of this research program, and really what me and small group of people in this field have set out to try to do 20 years ago is, can this be generalized? Can this be done in general? Not just for small molecules, but for materials, for large molecules, from molecular assemblies, including bond breaking and bond forming. So, we don't want to take a random molecule. This is, sulfur, nitrogen, oxygen, and phosphorus, appropriately hydrogenated, depending on the order, and you want to see what happens. Or you want to create a model of a battery. It's the anode, electrolyte, and the cathode, and just want to see it run and see what happens. So the idea of doing this with machine learning is that you afford yourself a few hundred, few thousand genuine electronic structure calculations, maybe in periodic box, maybe not, and you solve the electronic structure problem, and that gives you a set of points on a potential energy surface. And that you need to systematically and improvably interpolate. You do that with some kind of representation of the atomic environment. You do that and then you do regression. And we've learned over the last 30 years how to do regression. Import that from the computer science community, from machine learning community. You can do that with neural networks, with Gaussian processes, with regularized linear regression. And that gives you a candidate potential energy surface. And if it's good enough, you go and do the science. If not, you go back and get more data. And that's where universal approximators and theorems about regression are very helpful because you can monitor the convergence of this potential energy surface to using the training and validation data. So when you set out to do this, it all sounds fine, except that the question is, how many times do you need to go around this loop? How efficient is this whole process going to be? Because as opposed to typical machine learning tasks, we do actually have the ground truth here, and we can compute it. So if it took 1 billion DFT calculations to create a good potential energy surface for a material, then this wouldn't be very useful. We could just go and do our science with DFT. It turns out that is, although lots of people were afraid that this would be the case, it isn't. And you can go around this loop not too many times. And this has now essentially taken over how materials modeling is done. So this very brief graphical history, and kind of traces out what examples I'm going to give you in the talk, is, before 2007, which I'm not really going to talk about, is that here's the potential energy surface of, in general, it's just a sketch, of course. You take some data points in some minimum, and you can fit that. And there are many ways to do it. And you can only do it few minima at a time if you're using the sort of exponentially scaling quantum chemistry methods. But then came the seminal work of Jörg Behler and Michele Parinello in 2007 with high-dimensional fitting. And they devised descriptors of the local environment and used a simple neural network to do the fitting. But what it allowed them to do is to go in many dimensions, so 100 dimensions, about 30 neighbors influencing the force on an atom. And you can do a neural network fit that gives you the potential energy surface reasonably accurately near all the data points that you were put in the training data. But of course, not elsewhere. And the breakthrough, sort of the end of 2023, or basically last year, is the construction of models with very wide transferability. So very, very wide generalization, which is very unexpected. If you think of the machine learning literature and the sort of the lore there, how is it possible that I take data in a very restricted space, basically just inorganic crystals, and I get a model that is essentially chemically correct for an enormous number of a wide variety of systems? It must somehow capture something of the inherent structure of quantum mechanics. But I have to admit, and it's by the end of the talk, it'll be clear, we don't really know why this happens, but it's extremely useful. So let me show you what the sort of the middle part, what happens when you fit locally and get a good interpolator locally. This is an example from my own work, heterogeneous catalysis. This is the indium oxide surface. This is in collaboration with people from BASF. And we're looking at CO2 hydrogenation because it has been extremely well studied on this surface. And you have to build up a workflow. So this is something like what a workflow looked like 2 or 3 years ago. You take your system, the surface of indium oxide, you rattle it, you shear it, you put vacancies, you have individual molecules, and with each of these, you enter into an active learning loop to build up a data set. In the active learning loop, you train a model, you simulate something that could be MD, geometry optimization, large elastic band calculation of the minimum energy path for a transition. You look at that until convergence, you compute some uncertainty metric to see if it's converged. If not, you enhance your training set. All of that is done, and you move on to the next input, the next surface, the next molecule, and so on. And eventually, we started out by doing lots of MD. You then end up doing geometry optimizations and eventually large elastic band calculations too, and run this active learning loop. Altogether, we collect over 700 configurations. And by the time you do that, you get a potential that gives you a very, very faithful reproduction of the potential energy surface over this landscape, going from carbon dioxide here on the left to methanol on the right. And what you see here is the black lines are the lowest energy structures in each of these states, with the curves representing the minimum energy path. And the gap model, this Gaussian approximation potential, reproduces those minimum energy paths and minima energies kind of perfectly. And so, okay, what have you achieved? You've managed to reproduce the DFT work, and because it took a long time to develop all this active learning framework and learn how to do this, it took us about the same time as it took, you know, Dang et al. Originally to study this reaction set of reaction steps. But the point is that now you have a fast model, you know, 10,000 times faster than DFT. So you can do something like explore alternative pathways. So here's the path of the step of adding the second hydrogen to this carbon atom, and the normal pathway is this green one. Because we have a fast model, we can throw, you know, 10,000 different minima of all the slightly different local minima in the two different endpoints and connect them with 10,000 paths and find out which one is the lowest energy pathway kind of automatically. And when you do that, you discover an alternative path that is 40% lower barrier than the previously known best path. And after you found it, it's kind of obvious that this molecule rotates in the opposite way, and you add the hydrogen from the other side, the symmetry of the molecule is broken by the surface that's underneath it. But you wouldn't have found this if you just initialized the path by hand. So, and that now shows that this step is no longer the rate limiting step of this reaction. So, okay, this is useful, and but it's a heck of a lot of work. It's the PhD of the entire PhD of a student. But still, this is how people now do things, and there is a lot of material science that's now being done essentially in this manner. So I'm not going to go into the details of this, but here is you know, the PRL from Karsten Reuter's group, where they investigated the iridium oxide surface complexion. This is a catalyst material, but no, in this case, we're not interested in the molecules, but just what is the surface under different conditions. So different chemical potentials of the oxygen. It turns out that under sort of operating conditions, this is what I show here is the dominant surface structure, which is completely different from the as-cut surface, and this was not known before, and in fact is consistent with experimental images, TEM images of this material. So you can really do discovery, not of a new material, but of what your existing material actually looks like under your condition. You can do phase diagrams. This is a work a couple of years ago in Nature by Michele Ceriotti and his collaborators, where they investigate high pressure liquid hydrogen phase diagram as a function of pressure and temperature going to extreme conditions. And before, you could do phase diagrams, but it took extreme effort and huge scale compute, whereas doing it with the fitted ML potentials, it is a matter of weeks and months rather than years. And finally, this is work of Volker Deringer, who's a research fellow in my group, but the last couple of years, he's been a professor in Oxford. And he takes these simulations to a sort of extreme scale, the device scale. So now we really see this coveted point of merging of what we can do simulation in terms of length and timescales is the same length and timescales that experiments can access. So this phase change material, germanium antimony telluride, between these pair of electrodes, when you pass a current, there is amorphization and the recrystallization on the tens of picosecond timescale. This phase change material block contains 500,000 atoms, and you can go on a supercomputer, even the small ones that we have in the UK, and simulate 20 picoseconds and simulate the different pulse shapes of the current and study what happens to this material in kind of real time on the real length scale that is happening in experiments. So here's a pair of reviews which we've written in 2021. One of them, the first one spearheaded by Michele Ceriotti, is on the representations. So this is the atomic environment representations that underpin all of this modeling. And the second paper is on Gaussian process regression. It's how to use these models to actually do the materials modeling. Although we focused on Gaussian process regression here, many of the contents, much of the contents of this paper is applicable to neural networks. It's about how to build data sets, how to test models, and so on. So I'd like to have a slide with equations, and this is just to chart the development of descriptors, how we use descriptors introduced over 10 years ago. This is the smooth overlap of atomic positions and how they have evolved to the most modern descriptors that in the end will allow us a very wide generalization. So let me just go through that. So back in 2013, we used a representation of the atomic environment, which consists of building the neighbor density. So this is rho I around the atom I, and J are the neighbors, and you put a little Gaussian on each neighbor. You expand this density in radial functions Rn and spherical harmonics YLM with coefficients C. And I'm skipping over a lot of detail, but basically in the limit of sigma going to 0, this sigma here, these are just delta functions. And so the explicit formula for these coefficients is just the evaluation of R and Y at the neighbor position, and you sum over J. So this gives us a permutation invariant representation of the neighborhood. And then you get a rotational invariant, so a fully rotational and permutational invariant representation by taking these C coefficients and just squaring them. So C dagger C, it's a complex number in general. And you do C dagger C, sum over M, and you get a representation which we call the SOAP vector, and it has 3 indices, N, N prime, and L. So that was SOAP, and we did lots of, all the examples that I've shown you were done with this kind of representation. But in 2019, Ralph Strauss recognized that this construction can be generalized, and thereby some of its deficiencies fixed, and that's the atomic cluster expansion. So atomic cluster expansion is a generalization of SOAP, and it starts very similarly. We create this, I'm now switching to the notation of the ACE paper and then point out the similarities or the analogies. We take this phi, which is the pair basis, this R times Y is the same as what you see here. There's some extra indices. Again, I'm making contact with what's in the paper. So Zi, Zj are just the atomic numbers of atoms I and J. And these what we call the atomic basis is the sum over this pair basis over all the atoms in the neighborhood. So this is exactly analogous to these C coefficients. And then the analogy of the of this square here is a product of the A tensor. This now becomes a tensor, and instead of just taking a product of 2 C's as we did here, we can take a product, we can take 1 A or product of 2 A's or 3 or 4, and we indicate the maximum with this mu here. So that's the controls the maximum body order of the representation, and what the end result of that is this bold A tensor. And to get rotational invariance, we sum this over now not just M, but also L and M with Clebsch-Gordon coefficients. And that is, these are the analogies. So the A plays the role of the C, and this construction of the SOAP vector, the P from the C's, is really taking the product of the A's and then summing over L and M. And here there are Clebsch-Gordons in SOAP, but they're all 1, whereas in general, these Clebsch-Gordons are not 1, but there's a recursive formula for computing them, and they're written in the textbooks. So the B functions that we call the ACE basis are the permutational and rotational invariant basis for representing the geometry of the neighborhood. That's the general form of what we used to call here the SOAP vector. And Christoph Wörner was sort of instrumental in working out the mathematics of this in its full detail. And that was fine, and ACE was a much more powerful method than SOAP, and the ACE codes, again, due to Ralph's and Christoph's involvement, became much more efficient than the original Gaussian process regression that we did with SOAP. And in fact, the ACE basis is so much better, this generalized basis is so much better than the SOAP basis that we could just do linear regression. But now we do what we call MACE, which is even a generalized version of ACE. And it starts out very similarly. So we take a phi, we take the radial functions, the YLMs. We have a few more indices just because we can. So this is generalization. We take some atomic features that are not necessarily just the identity, but they could themselves have scalars and vectors and tensors, and hence there is a Clebsch-Gordon here. But then the next step is the same. We take phi's, we sum them over the atomic neighbors, J, that creates the A tensor. We product the A tensors with themselves, tensor product to create bold A. And from the bold A, we use Clebsch-Gordons to get the B. And that's the same as A's. But we don't stop here. We take these B's and we update atomic features, H, and we plug them back, and we do this one more time. So we go through this set of equations, not once, but twice. And that places this model into the category of message passing networks. And we pick up a bunch of tricks or freedoms from the neural network community, which is that we see these W's. Let me go back to here. So these W's here are degrees of freedom. They are linear matrices with optimizable elements that allow us to mix together the elements of this tensor. And this is how you build flexible neural network models. And so you train this with stochastic gradient descent. This model looks very closely analogous to the atomic cluster expansion, but the degrees of freedom that we optimize here get multiplied together. This is not a linear model anymore, like ACE is. So the W's have degrees of freedom. The R's here have degrees of freedom. So these R functions are small neural networks of a single variable, and half of the degree freedom of the model is in here. So this is a highly, highly flexible model. And it turns out, this is all the work of Ilyes Batatia, graduate student in my group. And it turns out that this model is much, much more accurate and much, much more flexible than either of the ones before. So let me show you two models that we make from this. These are now the generic, widely generalizing models. You can use MACE wherever previously you used GAP and ACE, so they can be used from scratch to fit any given specific data set. But what's really exciting is when you take a very large data set and fit a MACE model. So here's our attempt at organic chemistry. So you take the SPICE-1 data set. It's 1 million molecules and small clusters, 10 elements. And you fit a model. We have actually 3 different models, small, medium, and large. And we check how that model performs for new molecules. And the torsion benchmarking is one of the key things that you expect from a flexible organic transferable model. So this is taking these molecules that have two rings connected by a single bond, and you rotate one of the rings around it, and you look at the energy as you do that. And the target model here is black, but the gold standard that everybody accepts is kind of good enough for organic chemistry is the black coupled cluster with single, double, perturbative, triple excitations. And that's the black and the gray lie on top of each other. And so does the largest MACE model. So blue, green, and red is the small, medium, and large MACE models. And you see how you approach the correct answer for this unseen molecule. And for context, these other lines are other empirical models, and in fact, the ANI1CC, which is a machine learning model from a few years earlier. And you can see that they make large errors in this benchmark. And these are the averages. So if you take, I think this is over 500 different compounds like this, and it's the average barrier height error. And you see that the DFT here is about 0.3 kcal per mole of the gold standard, and the largest MACE model is almost the same. Now, let's see what happens when you go widely out of scope, out of domain with these models. And this is a molecular crystal benchmark. So the training data set has no crystals in it at all, just some pairs of molecules. And what you see is that ANI doesn't do very well, but the MACE, especially the large one now, the red circles, do really rather well here and reduce the error to about 7 kilojoules per mole. This is not quite good enough to do organic crystal structure prediction. You would need 1 or 2 kilojoules per mole, but there is no crystal data here at all. So I think this shows extremely good generalization here. One of the more later results that is actually already very useful is hydration-free energy. So this is the work of Harry Moore, a final year PhD student here. And I'm not going to describe the details of the simulation. It's completely standard. You take a molecule from gas phase through a series of lambda windows into a Hamiltonian that includes all the solvent, and you can compute the free energy that way. And when you do that, just focus on this block, which is the end result, the free energies of a bunch of molecules, free energy of hydration, going from vacuum to water. And experiment, this is something you can measure experimentally. In the experiment are the blue bars, and the small MACE model, not even the larger one, is the green. And it basically agrees with experiment for the right reasons. The potential energy surface is actually correct. Whereas empirical models, GAF is a very old one, OpenFF is a very new one, this is SAGE. For small molecules, they agree, but for large ones, they don't. Even though these empirical models have been fitted, their parameters have been tweaked to get the hydration free energy correctly. Since then, we've done this for larger drug-like molecules, and that works. That works reasonably well too. Here's now the materials side, which is the MACE model trained on the materials project. This is, many of you might know, this is an online database of 150,000 crystal structures, but altogether 1.6 million structures. They have been geometry optimized and then sampled. And so this is what it looks like. Periodic array of small inorganic crystals. 90% of this data set is between 50 and 70 atoms. So not very small, but not large either. And it's all periodic. 89 elements are covered, relatively small displacements from equilibrium. And so this was trained by friends of ours, by students at Berkeley, and with a small tweak from my students at the time. So this is going back to a year and a half ago, 2023. And the MACE model sort of jumped at the leaderboard that these students maintain. This is the Matt Bench leaderboard. These scores, F1 is the thing to focus here. It's basically the prediction of, is a material stable energetically, a new material? And all these other columns are essentially the rate of true positives, rate of false negatives, and so on, when you try to predict the molecular, the material stability. But then this kicked off some kind of race within the community, and within just 4 months, Google published their GNOME model, which, as you can see, made a huge leap in the ability to predict the stability of unseen compounds. So this is April 2024. Of course, they did that by upping the data set. So this is this is trendy in machine learning. So instead of 1.6 million structures, they went to 90 million structures in the training set, and that really allowed them to improve on this predictive power. But then sort of all hell broke loose, and you can see now models from Meta, which is this Equiformer V2, either on the original benchmark, on the original data set, or on 100 million. So again, 10 times bigger data set than the original one. And then there's Orb, which is a startup, MatterSim, which is the model of Microsoft, and they can get these excellent prediction results now for new materials. Look at what happens when you introduce a new kind of metric. This is kappa, which is thermal conductivity, the phonon contribution to thermal conductivity. And that's now not dependent on how well you predict just energies, but also forces. And that's a predictor for how well you're going to do dynamics. And this is now a number, this is the error in the thermal conductivity, a normalized error, and you want a low number here. And so the best predictor here is the latest MACE model, which is trained on just 3.4 million structures. The next best model is where is it? 4.2, 52. So that's GRACE, and that's essentially a re-implementation of the MACE model by Ralph Draughts. So the MACE architecture does really, really well here. Not decently in energies, but very, very, very well in forces. And some of the other models are really actually abysmal when predicting on forces. So okay, that's fine. That's materials discovery. But what if you're not interested in small inorganic crystals? What about general chemistry? And this is where the big surprise came at the end of 2023. We tried this model that was fitted to these small inorganic crystals, and just ran a simulation of a battery anode. And contrary to all expectations, it didn't explode when taken so far out of its training regime, but we got a nanosecond of stable dynamics. And then that prompted us to try lots of different things. All my students tried whatever was on their screen at the time. So amorphous carbon formation from quenching, polymerization of sulfur as you heat it up and pressurize it, hybrid perovskites, aqueous interfaces of various oxides and metals, combustion of hydrogen, heterogeneous catalysis that I showed you before. And emails started pouring in from kind of all over the world through the collaboration networks. And people were trying 2D materials, dislocations, ice and water, nanoparticles, molten salts. And it turned out that all of these systems, you could do stable MD for nanoseconds. And that was something completely new. So far, any chemistry that we tried, essentially MD was fine. And that resulted in this preprint, which is about to be updated. It had a long convoluted history in review at a couple of journals, but we are about to resubmit and update the archive at the same time, so you can look out for that in the next coming weeks. But here are some highlights. So the model does really well on things that are to do with water. So this is ice polymorphs, relative energies of ice polymorphs, which are, of course, in the training set, but we do get that really well. This is now the dissolution of salts into water. Surfaces and corners and edges of sodium chloride are not in the training set, nor is liquid water, nor is their combination. And this is the dissolution curve of a neural network potential that's explicitly trained on this model in large, expensive DFT calculations. And the blue is the foundation model just out of the box. This is nano-confined water, so two-dimensional water, and this is how you see trajectories of hydrogen ions moving through it, and this is the GOR of the original model. The latest tweak, which is part of the resubmission, gets even the first peak really, really well. So everything here kind of works. MOFs is something that's not in the training set, but if you check against the QMOF database, we get kind of exquisite accuracy of MOF energies, and this is the free energy of binding of CO2 inside a MOF 74, and this is again the off-the-shelf model compared with the DeepMD model trained specifically for this MOF using expensive DFT calculations. And you really need the machine learning model here. This is the UFF, the sort of original simple empirical force field. Doesn't get the binding energy right. And once you have off-the-shelf models, you can vary the ion, you can vary the linkers, and study the free energy maps of MOFs. And these are nanosecond long simulations for 91 different hypothetical MOFs. You can go and do materials discovery. This is catalysis, and what I want to show you here is fine-tuning. So for this catalytic surface, these are 4 different copper surfaces. These are 4 different steps of this hydrogenation of CO2. And what you see here is the foundation model is the orange, and the DFT is the dark red. And you say, well, it's not very good out of the box. There is an offset. So the binding, the foundation model hasn't seen surfaces, hasn't seen molecules. So there is an offset in the binding energy of the out-of-the-box model. But, these peaks and troughs are roughly in the right place. And it only takes a handful of new configurations to fine-tune. So you can do the exploration of the reaction network with the foundation model, even though the binding energy, absolute binding energy, is wrong. But once you fine-tune, you get this model that is the light blue one. And when you do the nudged elastic band calculation with that, and you reevaluate DFT on the nudged elastic band of the fine-tuned model, that's the dark blue. So essentially perfect reevaluation. And you see that this is climbing image nudged elastic band. So you see the barriers are exactly right with respect to the full DFT nudged elastic band. And here are the binding energies, right? So this is the PBE plus DFT binding energies of these 4 different fragments. The original model doesn't get them right, but the fine-tuned one, just with a handful of configurations, really gets you perfect binding energies. So really what I think we've achieved is foundation modeling that is that's not as accurate for everything as DFT, but is empirical quantum accurate, high binding accurate, stable for everything. And with a tiny bit of fine tuning, you get ab initio accuracy. And in that manuscript, you see 40 different applications in the supplementary. It's over 100 pages. You can see in detail how it does for all these different, all the different compounds with the speed that's 1,000,000 times faster for DFT on the small sizes. Once you go to big sizes, of course, the speed ups can kind of be arbitrary. So really, this is the closing slide. So I think we now have force fields for the periodic table, thousands of atoms, tens of nanoseconds, nanosecond per day. So in a couple of weeks, you can do tens of nanoseconds on the GPU, ab initio accuracy when fine-tuned with just a handful of configurations, and rather modest compute. So, we don't need OpenAI-sized tools to do this. To train a foundation model takes about 2,000 GPU hours. So, not trivial, but perfectly accessible to an academic research group. And really, what's enabled this is the huge diversity of the data set rather than just the raw number. We don't have a full understanding of what it is in this maze architecture that enables this stability that other architectures don't have. That's still under investigation. And what's coming next is charge self-consistency. How do we bring back the electronic structure? I think my presentation has stopped itself, which is just as well. And I'm ready to answer questions if there are any.
Thank you. Thank you, Gabor, for the excellent talk. So every time I attend your talk, I learn a lot. So let's come to
you saw a lot of slides again.
Thank you. Let's go to the Q&A session. So again, please feel free to raise your hand if you want to ask directly. Otherwise, you can always put into the Q&A box, and we'll try to go through them. We have plenty of time.
So I see 2 questions already. Can I answer them?
Yes. Do you want to go directly, Gabor?
Sure. So the first question is by Lenny Oren. Can I elaborate on why the Google and Meta models fail to predict kappa? We know a little bit about it. So some of these models, actually, the Meta models are publicly available. The Google model is not. And I think the Microsoft model is available. So we can test some of these. The Meta model is incredibly unsmooth. So if you look at that Equiformer V2, it's a transformer model, 30 layers of transformer, gazillions of parameters. I think it does well on energies, essentially memorizing the input in a way. Well, I'm sure they would say that that's not true, but it is very good in energies, but incredibly unsmooth. So if you take even just binding energy curves of atoms, you take an atom and you break a bond, and the binding energy curve is like this. So incredibly unsmooth as a potential. And I think that's the reason why the forces are terrible. The Google model is worse. It's not as bad as the Equiformer. I think, but I think it's kind of a similar story that it's quite nonlinear. What I really like about the MACE model is that it has nonlinearities in its radial functions. It has a tiny amount of nonlinearity in its readout, but not very much. It's almost linear. And the rest of it is products of polynomials that are well controlled. And that's what gives you extrapolation, and that gives you smoothness. These are gut feelings. These are not proofs. I think that this kappa RMSE was introduced a few months ago because people are realizing that, yes, I can get a good energy prediction, but that model isn't usable for anything else, isn't usable for computing properties. So I'm sure that people will make models that are improved on forces, and we will learn a lot in the coming years about how to do that. And we will learn why MACE was so good. The next second question is, what is the bottom line or the number of data points needed for fine-tuning? Well, I don't have a bottom line, but we're preparing this resubmission, the updated version of the MACE manuscript, And in every application, we've gotten excellent fine-tuning results with 100 new configurations. That's not a minimum. It's not, I wouldn't say it's the tip, is not a guarantee that you will need that many, but it's a very good number for a typical application. So when I say a handful, you know, it could be 20, could be 100, but on that order, you get excellent accuracy, and you retain the stability of the original foundation model.
So Gabor, there are 3 questions related to the uncertainty quantification in maze in general. Can you answer them just broadly together?
So sure, I can talk about uncertainty. So the ensemble models is implemented in maze. So there are various versions of uncertainty implemented in the maze architecture. You know, last layer ensemble, linear prediction, you know, sort of drawing from the Gaussian distribution of the last layer linear. There's lots of different ones, and of course you can just use different seeds, and so those are all in there. I think that while we were doing a lot of active learning, which I showed you in connection with the catalysis, a lot of iterative training, I think that uncertainty prediction was really, really very, very important. It was at the heart of any active learning loop. And so a lot of work was done, mostly not by us, in this field community about what are different protocols, how do you estimate uncertainties. Personally, I'm kind of a lot less interested in uncertainties since foundation models have become so generally useful. And that is because we don't do so much active learning. If you look at the active learning, the foundation models, they've not been trained for most of the case. They would say they are uncertain in most places, but doesn't matter. You still run them. The models are stable. You collect configurations, and in one shot, you get you get a new model, and you don't need to look at the uncertainty. You just randomly sample your MD with the foundation model, and that seems to be enough. At least that's what we see now. There is a huge amount of background theory in statistical learning about uncertainty, so it's not going to go away. And it'll be very interesting to see what is the optimal way of using uncertainty quantification in conjunction with foundation models. And I think that's still sort of yet to be seen. But they are implemented in the maze framework.
So Gabor, can you go to this question by Qin Wu?
This is the so you've seen that the curvatures, I guess you mean curvatures, are quite different in the bilateral torsion example between the maze and the CCSD. So I'm not sure exactly what you mean. Let's go back to that. So let me share the screen again. So let's see. You're talking about the curvatures, but the red line is the maze here, and it's right on top of the couple cluster. So I think what you see is that when the maze is small and medium, then the curvatures, the barriers are off, and that's of course is related to the curvature because these models are very smooth. But by the time you reach the large model, which has a larger there are two things that are changing when you go from small, medium, and large in this work. One is the cutoff. So we go from a layer cutoff of 4.5 to a layer cutoff of 6, and we increase the number of channels. So the overall flexibility of the model is increased, and to about 4 times. And that the large model now rise completely on top of the coupled cluster result. Do you want to pick Hongyang?
Yeah, you can go to maybe this following one about enhanced sampling in simulations. So just follow the question by Qin.
Okay. This is all right. So yeah, sure. Can the model be used for enhanced sampling? I mean, it is already being used. And especially the foundation model, right, where you are going in enhanced sampling, you're really trying to go to sort of very different different places in configuration space where you haven't been to. And you can use MACE via its LAMPS plugin in Plumed. And I've seen beautiful metadynamics and well-tempered metadynamics calculations by many people using the MACE foundation model and the MACE-off model coupled with Plumed and the huge variety of collective variables that it makes available out of the box. So that's, I think, we are doing that in a small research project on solvated transition metal ions. But I've seen lots of other people use that in many, many different contexts. And I think that is the point of the foundation model, is that you expect stability in everything. Now, I mentioned at the very end that we are now working very hard on putting electrostatics into it, which will enable an exploration of different oxidation states. So that is, you might choose coordination and oxidation state as one of your collective variables. And the foundation model, as it's released now, has learned an oxidation state essentially from the materials project. And you will not be able to, it will get pKa's of organic molecules quite wrong, I think. But if you try to do the free energy calculation of the pK calculation, but that's when we come to do electrostatics, which then has the notion of charge and amount of charge on certain atoms. That's the next step for us.
Mm-hmm. Yeah, sort of related question. So they're asking are the models capable of capturing long-range interactions, including electrostatics?
That's right. So it's very the history of long-range interactions and ML potentials is really quite interesting, because ML potentials have kind of made most of their impact in material science rather than organic chemistry. And in material science, these models that, like GAP, ACE, and MACE, that don't exclude explicit long electrostatics, but include it implicitly as far as the cutoff allows. So an ACE model with 6 angstrom cutoff will have Coulomb interactions up to 6 angstroms. A MACE model with 12 angstrom receptive field will have effectively capture a Coulomb interaction up to 12 angstrom. Goes a very long way in material science. When you go to molten salts, solvated ions in water, you can design observables that are just wrong. And you cannot get them right for deep physical reasons without having an algebraically decaying Coulomb interaction. If you build a slab model of water with any short-range model, be that ACE or MACE or anything else, you will find that the dipole moment of that model is growing as a function of slab size, whereas which really isn't physical, that you get dielectric breakdown. Whereas if you had a model that includes a formal 1/r interaction, then the molecules will align themselves such that you don't get you don't develop a large dipole moment. So that's why we are working on but you don't see this if you only do bulk, right? So bulk water modeling is perfectly fine because you train it on bulk, you predict bulk, it's all implicit. But if you want to then go on to do interfaces and surfaces, then the physics tells you that you have to have the long range interaction formally as 1/r. But it's really those niche questions. But for some people, they may be the question they immerse themselves in. But what I'm trying to say is that you can do a very large amount of things with implicitly describing the charge, but not everything.
Mm-hmm. So, Gabor, can you quickly mention about the capability of MACE? Is it integrated with LAMPS and
Yes,
also can model defects?
Right. It's integrated.
Complex
we use
materials.
it with ASE and with LAMPS. We have CUDA kernels that give you large factors of speed up. NVIDIA recently released an Q-equivariance, which is their kernel for computing spherical tensor products, hand-coded for NVIDIA chips. And for the large MACE model, it gives you a factor of 5 in both evaluation and training. So we use that, and that works well with PyTorch. At the moment, MACE runs, formally, it runs really well on a single GPU. I didn't include the performance benchmarks, but we can get 10 nanoseconds per day on a single GPU. When you do multiple GPUs, the currently released versions are not very efficient, but we are very close to releasing a multi-GPU version that will do a nanosecond per day on 60 GPUs, hundreds of thousands of atoms. We can do the same on a CPU. So the COCOS framework that LAMMPS uses can let one compile a parallel code, both multi-GPU and multi-CPU. And we've done million atom CPU-based simulations with MACE. Again, nanoseconds per day. So those are soon to come. We are sort of testing them in-house already.
Mm-hmm. So can you maybe a couple of questions related to the fine-tuning? It's quite important for MACE. So can you talk about the general guidelines and anything we need to pay attention to fine-tune it?
Mm-hmm. So the protocol is that take a small example, small in terms of number of atoms, of what you want to simulate as close as possible. So and it has to be small enough that you can eventually do DFT on it. Simulate it with the foundation model, long time, enhanced sampling, whatever you're trying to do, high temperature, high pressure. You collect configurations. At the moment, we've done that randomly, or maybe stratified, certain pressures, certain temperatures. You get configurations, a handful of them, a couple of dozen, maybe 100. You compute DFT on them, and you don't even need to use the same DFT as was used for the foundation model. The only important thing is that you also compute the isolated atom energy, because our recommendation is that you use MACE to always fit the binding energy, the atomization energy. So difference between isolated atom and the structure. So that's what the MACE models that we release are targeting. So when you input new data, you need to compute the isolated atom with your chosen DFT method. And you plug that new data into the fine-tuning script, which is published as part of the MACE package. And that implements what is called multi-head fine-tuning with replay. So the new optimization takes some of your new data and some of the old data, and it creates a readout head on the model, one specifically for the old data and one for the new data. And all the parameters can change. But this means that you will have a readout head that's specifically optimized for your new data, but most of the rest of the model is restrained to reproduce the part of the old training data. So you don't overtrain. So you don't specialize too much to the handful of configurations that you produce. And we had a lot of success with this kind of fine-tuning effort. But this is just the beginning. So I'm not claiming that this is the best way or the only way. Lots and lots of papers are now appearing on the archive in which try to fine-tune the model.
Mm-hmm. Yeah. Another question is, I think it's still interesting about the long-range interactions. So this is asking, is it reasonable to predict charges using short-range embeddings, and then use the EVAS method to capture the long-range Coulomb interactions?
I think that depends on the system. So that's not reality. So charges in DFT, if you think about how the charge density is optimized, that there is induction. So the charge partitioning that happens across a bond is influenced by the local field, and that local field is a result of all the charges in the system, not just the local geometry. But there will be special systems where these effects are small. I'll give you an example. If you take water, including charges, so H3O plus, OH minus, solvated ions, sodium, chloride, the partial charges that very well describe those systems is mostly a function of the local environment, and screening is quite good, and so you can get away with predicting local charges from the environment. I'm personally less interested in that. So what we're trying to do in the work in my own group is to do a sort of full self-consistent model where we actually take the local field into account, predict the charge, local charge as a function of geometry and field, and then iterate. There's a bit of extra cost involved, but I think that allows you to then correctly model charge transfer and very challenging applications like electrocatalysis, solid liquid interactions under field is what I'm interested in, and for that you need the full self-consistency.
Mm-hmm. Yeah, we are almost running out of time. Maybe we'll take one last question from the audience there from Miles. He's basically asking about the size of model and the architecture model. So what's the future?
So that's very interesting, and that's exactly, and you scrutinize those different model sizes, what's there is when we produce MACE models, we always make small, medium, and large to explore that a little bit, and often the small models are not that much worse than the large ones, but there is a little bit of a marketing thing here, is that when people look at the bold numbers in the tables, often they produce the large models, and then when people talk about how fast their models are, they look at the small models. Because both of those are legitimate. I think what's very interesting about this question that Miles is putting up is what happens as you get more training data. So if you look at large language models, one of the trends that we've seen over the past few years is that models got better when the size of the model went up. But that's not what we see so far in the foundation models, in these widely generalizing models. What we see is that models get better when you put more training data without changing the size of the model. So actually, the MACE model that was trained on Mathilde's project, originally 1.6 million structures, is the same size model that we trained on OMath, which is 100 million training data. And the errors became much, much lower without the model size going up. So I'm not saying that that's some kind of theorem or that will never change, but I think that's really, really interesting. And as we try to make models get more smaller memory footprint, squeeze out more performance, learning how to make smaller models give the same performance, perhaps trained on very large data sets, I think will be a very, very interesting direction.
Mm-hmm. Yeah. So Gabor, speaking of a large language model, I want to ask you maybe the final question, since we are running out of time. So given this recent rise of this mix of expert strategies, like in DeepSeek R1 model, so do you envision the future of this field, machine learning, internal potential, as relying on one large universal model, or sort of a mix of specialized models tailored for particular chemical systems?
I mean, we talked about this fine-tuning a lot, right? So I think that a model trained from scratch on sufficient amount of data, or a model fine-tuned on sufficient amount of data, will always be better than a generalist model. The question is, what is the overall effort required to get that? Will it be fashionable to still do one's own DFT calculations or not? I'm sure there will be some applications where it's worth doing that, but it depends on what style science you're after, right? Before, when we do DFT, and still when we had no foundation models, doing a completely new kind of application meant a PhD student, one project, one student, one application. And I think there will be some cases when we want to do that, but I think most students won't want to do that. They will say, let's take a foundation model, do the kind of science for which that works well with a little bit of fine-tuning, and I can start doing my application 2 weeks after I started it, not a year after. The first potential that will be sensible will be weeks, not a year. So that is such a huge step in the efficacy of a group doing science, that I don't see any way back from that. I can't see anyone building databases and fine-tuning models for a year before they get their hands on some application. It'll just be seen as not worth it. That's my prediction. We'll see.
Thank you, Gabor. So there's no better place to end the seminar. So thank you again, Professor Csanyi. This is really excellent talk and deep insights.
Thank you very
I've
much
also
for
thank
the
everyone for
huge range
attending.
of questions. Very nice questions.
Thank you. Yeah, thank you. Hope to see you next time.
Okay,
Bye-bye.
bye-bye.